Want to understand RAG and actually build something with it fast. In the next 16 minutes, you learn what RAG is and key features of an AI Copilot for which the full code is on Google Colab and shared in the description below. Let's jump in. What we'll cover in 16 minutes. First is a quick introduction into what is RAG. Next, we will have a walkthrough how a real RAG minimum viable product MVP works at a high level. We won't go deep into code here as a link to the full code on Google Colab is shared in the description below. We will explain key building blocks. Think of this as an example blueprint which can be further customized or extended to suit your needs. The term RAG can be expanded to Retrieval-Augmented Generation. There are two parts or components of a RAG: the answer generation component and the information retrieval component. Examples of some mainstream answer generation tools are ChatGPT, Claude from Anthropic, Google's Gemini, and Perplexity AI. They all make use of their own proprietary large language models, LLM, to generate the answer to your query. Since LLMs are powerful reasoning machines built on extremely large amount of data, why do we still need an IR? LLMs are built on static knowledge, based on the cutoff date the LLM was last trained on. In this example, the LLM was trained on data as of 2nd April 2026. Next, we run through a few example scenarios where an IR is needed to complement the LLM. Let's say you have a smartphone, which is a powerful device, but you will need it to access the internet to get real-time information. Similarly, for an LLM, we sometimes need to give it real-time new data for it to provide accurate answers to your queries. Now, for a car, if you need to send it to a mechanic, it would be good if you can also provide the mechanic with the car's historical service records so that the mechanic can review and provide a more targeted maintenance. For an LLM, this would translate to providing it with private or proprietary data to reason with. If you recently bought, say, a new AI lawnmower to cut grass, but you don't know how to operate it even though it is AI driven, you need a user manual. For an LLM, this is a classic example where domain-specific data is needed for it to provide precise answer to your query. Let's assume you are a tourist in an unfamiliar location and you ask for directions from a passerby who may or may not provide correct directions. It is much better if you can also access verified data like a mapping application on your phone. LLMs have this tendency to generate false information, which we refer to as hallucinations. We can counter this limitation by storing verified documents in the IR, which the LLM can use to reason and cite during answering. This would make the answers audit ready. This Copilot demo is targeted for use in a hydraulic rig. Imagine a scenario where a technician sits in a hydraulic rig control room and sees an alarm for pump leakage. He might need to look up a 200-page digital manual to search for information. There might be numerous mentions of it there, and he would need to cross-reference it with the sensor readings manually. This could easily take between 20 to 40 minutes depending on the technician's experience. On the other hand, If we had a RAG Copilot, by just asking a question, the pump leakage has increased. What are the likely failure modes? The Copilot would instantly retrieve the right manual sections, read current sensors, and generate actionable steps with chapter citations. This would then take around 5 seconds, which tremendously reduces downtime costs. There is no one-size-fits-all for building a RAG pipeline. We can have many variations positioned for specific requirements. This 5-step RAG pipeline, which is being demoed here, is just one example of many possibilities. First, we classify the question type. Second, we expand the query. Third, we do a hybrid retrieval from the IR which has both our manual and sensor data. There are also other data stored in the IR, like maintenance logs and knowledge base, but we are focused on showcasing just the manual and sensor as they are a bit more complex. Fourth, we re-rank and boost the retrieved information. Fifth, we generate the answer with citations using an LLM. The whole pipeline runs in 5 seconds on a laptop. Both the manual and sensor data are split into chunks stored in the IR. For the manual, we use a semantic chunker that splits by sentences, keeping 500 tokens per chunk with a 100 token overlap. This preserves meaning and context. For sensor data, we don't semantically chunk as that would split numbers into chunks. Instead, we manually create 2 chunks, one for current readings, one for thresholds. Each is about 50 tokens. A token can either be a word, number, or punctuation. Let's look at examples. This is a truncated example of a manual chunk. This is a truncated example of a sensor data chunk having current readings. Step 1. Query classification. We use 5 flags here. The first 4 are troubleshooting, procedural, definition, and maintenance. If none of these 4 flags are being identified, we would then classify the query as general. We will show partially how it works for the troubleshooting flag. First, it looks for signals, keywords which we have pre-configured. Troubleshoot is one of the signals which is not found, but we did find failure, which is a strong troubleshooting indicator. Hence, we flag the query as troubleshooting. We also do the same for the remaining except for general. We are skipping through here, but know that we went through the same process and did not find any signals for procedural, definition, and maintenance. Since we have one flag, which is for troubleshooting, the general flag is also not used. The result, the query is classified as troubleshooting only. Step 2. Query expansion. We use 3 approaches in parallel: SPLADE, corpus co-occurrence, and chapter affinity. SPLADE adds morphological variants like increase from increased and leak from leakage, so we catch all forms. Corpus co-occurrence found that pumps appear near leakage in 70% of cases. Chapter affinity maps pump leakages to chapter 4, 10, and 9. The expanded query is now much richer. When we search, we'll find content about pump slippage, internal wear, seal failure, exactly what we need for failure modes. Now let me explain our hybrid retrieval approach. We take the expanded query and run 2 searches in parallel. On the left, dense retrieval using Qwen 3, 0.6 billion, embedding model. It finds conceptually related terms like plumb slippage and internal leakage, even though those exact words aren't in the query. On the right, sparse retrieval using BM25, a classic keyword search algorithm. It finds specific phrases like chapter 4 and volumetric output. For the dense retrieval, internally what happens is the query is converted into a numeric vector and search against the chunks in ChromaDB for semantic meaning. ChromaDB is one of the available open source vector databases that are being used for RAG. For sparse retrieval, the query is being tokenized and search against an inverted index for exact term matches. The inverted index is a file that is loaded into memory when being searched. This is different from ChromaDB. We use a hybrid storage to get the best of both. Then we fuse the results. 60% weight to dense, 40% to sparse. Why these weights? Because semantic understanding is generally more valuable, but exact term matching is critical for finding specific chapter references. The output is a ranked list of the top 30 candidates, which then go into our re-ranking stage. Step 4. Re-rank and boost. Every chunk from the manual is tagged to a chapter number, section, and chunk type. Here, we are only showing the chapter number and chunk type, and we left out the section tag. The chunk type is used for boosting. For the top 4 ranking chunks shown here, we see 2 different chunk type tags, troubleshooting and original. Since the query is also tagged as troubleshooting, the chunks tagged with troubleshooting gets a boost of 1.3. For this chapter 4 troubleshooting chunk, it gets a boost of 1.3 and its value increases from 0.775 to 1.008. Similarly, the chapter 3 troubleshooting chunk gets a boost of 1.3 and its value increases from 0.713 to 0.927. After this boost, the chapter 4 troubleshooting chunk remains at rank 1, while the chapter 3 troubleshooting chunk moves up from rank 3 to rank 2. Here's exactly what gets sent to the LLM. The instruction being sent to the LLM is referred to as a prompt. The prompt we are using has 5 parts. First, the system instruction. You are a hydraulics system expert. Notice this portion does not have any labeling. Second, the manual context. It starts with the labeling and colon followed by the 5 chunks retrieved by our hybrid search, each tagged with its chapter and section. We are only showing part of one of the chunks here. Third, the available chapters list. It also starts with the labeling and colon followed by the chapter list. The chapter list is sorted by relevance so that the LLM knows which chapters are most important. Fourth, the user's original question. It starts with the question label and colon followed by the question. Fifth, critical instructions. It starts with the critical instructions label and colon followed by the actual instructions. It tells the LLM to cite chapters and provide failure modes. Of these 5 parts, only system instruction and critical instructions are static. The rest change according to the question being asked. The full prompt with all 5 parts are sent together to the LLM. Once the LLM gets a prompt, it generates an answer. The LLM we are using is from DeepSeek, specifically the DeepSeek R1, a distilled version with only 1.5 billion parameters. Over many iterations, we tried other small LLMs, but this seemed to outperform the rest. Some reasons for choosing this LLM include strong reasoning for diagnostic questions, a small footprint to run on a laptop. We can run this on Google Colab. Fast inference for real-time response. Zero cost since it's run locally and open license for commercial freedom. We now look at the final answer being generated by the LLM. The answer cites Chapter 4. This is important as it shows grounding in the actual verified documentation and there is no hallucination. The answer also explains the key technical term from the manual, pump slippage. It also provides differentiation that a technician needs to know to diagnose which failure mode applies to their specific pump type. Do review the link to the complete Google Colab code for this Copilot in the description below.